Welcome everyone to this three-part web series on event-driven microservices with Apache Pulsar. So this is part one. My name is Yannis and I'm a solutions engineer here with StreamNative. And along with me, I have Karen, Tim, Don, and my co-host David Kermgaard, who is also the author of Apache Pulsar in Actions, a book recently published by Manning Publications. And without further ado, David, I'm going to hand it over to you to introduce yourself and get us started in this world of event-driven microservices with Apache Pulsar.
Sure. Thank you so much, Yannis, for that wonderful introduction. My name is David Kermgaard. I'm a developer advocate at StreamNative, and as Yannis mentioned, author of the book Pulsar in Action, which a lot of this content is based around. Welcome to the webinar, and let's go ahead and get started. So as Yannis mentioned, this will be a three-part series. So obviously this highlights what's going to be covered across the three different parts to give you an idea of what we're going to focus on today. We're going to start with a background of Pulsar itself, just a basic introduction and an overview of the terminologies. I'll be using some different terms. I want to make sure everybody's familiar with those terms before we get too far into the presentation. Next, we'll take a moment to do some background information on Pulsar functions and what they are, some of the benefits they perform and they provide as far as microservices are concerned and in general, and discuss the programming model a little bit, how to think about building your Pulsar functions, how they interact, the inputs, the outputs, things of that nature. Then we'll take a moment to do a little bit of theory just on microservices themselves, focus on the goals and characteristics of what they are, what they're intended to do. Some of the different communication styles that they're used to interact with one another. Obviously, as you break the monolith into smaller pieces, it's critical that these smaller microservices and pieces are able to interact with one another. And we'll focus on some of the communication styles that are available and how we can implement those using Pulsar functions. And then lastly, we'll conclude that section focusing on why Pulsar functions, in my opinion, is a great fit for this technology. And then we'll focus on an event-based microservices application, getting to the real meat of this webinar, part one, by showing an actual use case, a food delivery use case, focusing on the API design, which is the contract that supports all the different interactions between these microservices. And then I'll hand it back over to Yannis, who will do the hands-on development, deploying and running of these microservices and show you some of the code that we have and we're going to make available for you today. Part two, we'll expand on that using stateful microservices. We'll expand on this existing use cases and get into different state storages within these functions rather than stateless, and get into some of that information. And then part three, we'll focus on integrating Flink as well into the application, so you can do some real-time analytics on this different data, doing mergings of streams, more interesting analytics as well. And Tim will be providing that. Tim, along with Addison, the Chief Product Officer, will be providing that. So that's just a background on where we're going to go over the course of this three-part series. So without further ado, let's start part one of building microservices with Apache Pulsar and focus on some of the objectives for this particular webinar itself. So again, as I mentioned, we're going to introduce what Pulsar functions are. So hopefully after the end of this webinar, you have at least a basic understanding of what they are and some of the benefits that they provide as it pertains to microservices development. And then focus a little bit on what event-based microservice architecture entails and how that's different from RPC-based microservices architectures. Then I'll hopefully understand or convince you that how Pulsar functions are a great tool to use for microservice development, and then describe some of the benefits of schema development within microservices, right? So obviously interaction, again, requires implicit contracts, and we'll focus on how to implement that using Avro schemas in this use case. Then, as I mentioned before, we'll dive into the development, building an actual microservice using Pulsar functions. So that's the real code that we have sitting in the repository for you guys to look at. And we'll outline the steps required to, once you've built that microservice, to actually deploy it to Apache Pulsar. And then finally, to be able to monitor it, to demonstrate how, data flowing through that microservice, how it's interacting. You can get some metrics on how long the processing latency, if there's any exceptions, things of that nature. All of that is built into the Pulsar functions, and we'll demonstrate all those different features as part of this webinar. So let's start with module 0 and just focus on Apache Pulsar itself and make sure that you understand some of the key terminology used within Pulsar. So I start throwing these terms around, we're all sort of on the same page as far as that goes. So let's start with a very basic one. What is Apache Pulsar, right? We have this big marketing spiel that basically says it's a cloud native messaging and event streaming platform. So what does that really mean? When we're talking about, so let's dig into cloud native first. Let's parse this message down, the sentence down into three pieces. Cloud native means that it's designed to run on elastic cloud environments and across a variety of hardware. It was designed to run on Kubernetes first and foremost, and that's done through stateless serving layer and a redundant reusable storage layer being separate pieces. That allows us to basically add broker components and bookie components or storage components independently and react based on the demand in real time without any sort of rebalancing or reshuffling of the data that's required from other platforms such as Apache Kafka. Secondly, we also mentioned messaging. So it's one of the few platforms that support the messaging use case, which is pub sub, your traditional messaging capabilities that are available in things like RabbitMQ, things of that nature, where you have one, a topic and a subscription or multiple subscribers, allows you to do one-to-many sort of publications and stateless messaging processing. But it also provides event streaming platform as well. So not only is it messaging, but it's also streaming, which is a low latency and long-term event capture, storage, and processing. It's conceptually similar to Apache Kafka, where you can queue up the events, maintain them in a time series order, and then do analytics on them later or process those messages later, rather than in a reactive manner. So Apache Pulsar is, again, it's an open source project because it's Apache, and it provides all these messaging capabilities in a cloud native messaging platform. So moving on here, hopefully. So some of the key terminology that we use inside of Pulsar, just so that when I start throwing these terms around, we're all on the same page. First, we'll just start with producers and consumers, right? So producers, any process that publishes messages to a Pulsar topic, right? It's any application, any service that plays that role of I'm sending messages out, I'm communicating to other people, and I'm broadcasting a message. Conversely, a consumer is any process that establishes a subscription to a topic and processes those messages. So producers produce, consumers consume and receive the messages. Brokers are a term for those intermediate layer of part of Pulsar that handles the connections and routing of the messages between the producers and the consumers. All interaction in Pulsar ultimately goes down to the brokers, and that's who handles all that handoff of the messages. Topics, the term topic is really just a named channel for transmitting the messages. It's a logical storage location for messages to be handed off between producers and consumers. And we also support partition topics, which are virtual topics composed of multiple topics under the cover. So it can be done transparently to you. You don't have to know which partition you're consuming from. From a consumer perspective, it's one logical topic, although it's implemented under the covers as multiple topics. Next, the term message just is anything that belongs to a topic and contains an arbitrary payload. Just think of it as raw bytes and some metadata included with that. So you can send any you can send strings or integers or serialized JSON objects, for example. Ultimately, they always contain those bytes and some metadata, again, around like message ID, the event time, things of that nature. Also user-defined metadata that you can be attached to those. And that's what's stored in the topic. The next term is Pulsar Instance, and that's the largest logical grouping within Pulsar, and it's considered a group of clusters or multiple clusters that can act together as a single unit. This is allow you sort of things like georeplication, where you can have topics in multiple regions, but they all belong to the same instance, and that way you can manage them and maintain them as one logical instance rather than having several clusters that you have to maintain independently. It's a logical higher level than a cluster. Now, Pulsar cluster is just a combination of Pulsar brokers, bookkeeper bookies, which are used for storage, and a zookeeper quorum that stores the metadata that has all the different policies and information around where the bookies and brokers are communicating with one another, where the data is stored, and things of that nature. That's one logical, geographically co-located collection of services and cluster and information that forms a cluster. Next is the concept of tenants, which is just, we support multi-tenancy. Pulsar supports multi-tenancy out of the box. And it's an administrative unit for allocating capacity and enforcing authentication authorization. So it allows you to define who can access certain data topics within a certain, namespace. You can sort of cordon those off for, certain access rules. So you can make sure that people in one group cannot access private sensitive data that don't belong to that group. And then lastly is namespaces, which is just an administrative grouping mechanism for a lot of related topics, because Pulsar can support over 2.8 million different topics at any given time, and obviously setting policies and retention policies, security policies for those would be an administrative nightmare if you had to do it millions of times. So you can logically group them into something called a namespace, and then apply a policy that applies to all of those within that namespace. It allows you to do hundreds or thousands, manage hundreds of thousands of topics with a single command rather than having to do it individually. And all topics are addressed as a tenant first, then a namespace, and then finally a topic name. So they're logically grouped and nested in that manner. All right, showing that information graphically looks something like this. So a producer role is anything there on the left that sends data to the Pulsar broker and specifies a topic that it's destined to be written to, and it's completely decoupled from the consumers. That's the key here. It just publishes to broker, and the broker on the other side is the consumer role, is any process that can receive data and never directly interacts with the publisher, right? So again, it just subscribes to a Pulsar topic and says, I want the data, and Pulsar makes sure that information is provided. It's important to note here, as we'll see, that these are just roles. So it's possible that an application can play the role both a producer and a consumer, which in the case of an event-driven microservices is exactly what you need, right? The producer, somebody upstream is going to send messages to you as a microservice. You will be a consumer first. You'll get triggered by the event. You'll then react to it, and you'll want to broadcast your results as a producer to a downstream target topic that again triggers that event for another microservices, which is acting as that role. So it's a very common practice in event-driven microservices that you'll play both roles in that scenario. So having set that background, let's talk a little bit about, give you some background about how you would normally develop an application using Apache Pulsar, using the more traditional approach, right? If you want to write it all in a single application, or you want to use like a Spring Boot framework and you wanted to make sure that you got messages and then did business logic and published messages as well. Basically, you'd have to be able to write an application that uses the Pulsar client library and the APIs in order to send and receive messages. So right now, currently supported, the Pulsar client API has official language bindings and support for all these different languages there, Java, Go, Python, and these different ones. There's also some experimental ones or non-officially supported ones for multiple languages as well. But in general, the client API, regardless of which language you're using, sort of provides these features, right? It encapsulates the client-server communication protocol, the low-level bytes of sending and consuming the messages. So your application logic doesn't have to concern itself with that. It adds some additional features in Pulsar primitives and exposes a simple API for the applications to use for publishing and subscribing. You say, I want to produce messages, I want to receive messages, and it sort of provides an abstract API for your applications to do that. The client libraries themselves handle a lot of sort of all of the underlying nasty details of interacting and sending the messages directly to the broker. They support transparent reconnection and load balancing for failover. So you just say, send a message. If that broker is down for whatever reason, it will automatically retry it for you. And you don't have to be notified of that or be cognizant of that in your code and have a try catch block to have to deal with, connection failovers or things of that nature. All that is handled for you by the client library. So it's very convenient. They provide connection pooling, batching, and other features that are very useful for you. That makes your job easier as an application developer. So let's look at the very basic use case of getting started with this, right? This is the basic Java API for building a Pulsar client, right? You basically use the builder pattern. At a minimum, you have to specify the service URL. What you're saying is this is the port, this is the server and port that I'm going to send messages over using that binary protocol. And similarly, C# does it very similarly. This is sort of a minimum requirements. You can obviously, if you're going to a secure endpoint, you would have, there's APIs to add, authentication mechanisms, security credentials, configure some other additional, connection pooling, things of that nature that are available to you as well. It can all be done with this API, but this is the bare minimum requirement in order to connect and create a Pulsar client. So let's look at first being the producer on the producer side, the left side of that diagram that we saw earlier, right? This is the minimum code set up to do that, right? You first create the Pulsar client, as we saw, supporting providing the service URL. Next, you have to use that client to create what's called a new producer. And you specify the schema type or the data type that you're going to send, the topic, again, that's the minimum that you want to send it to, and then you create that producer. And if there's any problems at that point, an exception will be thrown. But assuming that goes through correctly, you can then use that producer to send messages as shown at the bottom there, right? So you can say new message, You can provide a key if you want to. You can provide some of that metadata if you want to, but the very minimum is that value call right there. You specify whatever value you want to send. And then lastly, you invoke that send method, which is a synchronous call in this case that forwards the data to the broker persists it to disk, and then it sends an acknowledgement back that it received the data and you can proceed on. There's also an asynchronous one as well, which you can sort of trust that it gets there, but this is the minimum. This is how you traditionally send messages using an application in Java. Similarly, on the other side, to be a consumer, again, you follow a very similar pattern, right? Step one is to create the client, as we already saw. Step number two is to use the client to create a new consumer. Again, you have to specify a schema that says, hey, I'm expecting strings back, and the Pulsar will convert the bytes and that raw bytes and that payload back to a string for you automatically. You have to specify the topic that you want to receive the data from. And you also have to provide a subscription name, which is sort of a unique idea of keeping track for this particular consumer where they are in the messages, because you can have multiple consumers on different subscriptions reading that information from the same topic. So think of it as a unique ID for just this particular consumer to keep track of where they were. Assuming that that consumer is created, this is sort of a traditional while loop and where you can continue to receive information, right? So you're always doing a call to receive, which is a blocking call on that. And so you wait to get the next message. Then you would take that message value and do some business logic on it. And then finally, when you're done and you didn't have any errors and everything went successfully, you would call the consumer and acknowledge receipt of that message. And that would basically move your logical pointer forward in the topic to say, okay, in your subscription to say, okay, I'm done with this message. I don't ever want to get it again. I'm done with it, right? So that ensures that you do, exactly one sort of processing. And those are the steps required just to do that in a logical message consumption pattern. So putting all this together, if you wanted to have a microservice that was event-driven and you wanted to have an application that plays the roles of both a producer and a consumer, this is sort of the boilerplate code you need to set that up, right? As you can see, it's about 16 lines of code, right? Just to get at the business logic here halfway down. Well, to do all of that, there's a lot of wrapping code to do. It's very inconvenient to do, but it's the basis of how you do it. So hopefully that you get a feel for what all that entails. But as you can see, if you want to do event-driven microservices, the client API allows you to do that, right? But to send the producers and the consumers, but it requires a lot of that boilerplate code, as we just saw, right? And when your real focus wants to be on the business logic, you don't want to have to set this up every time and redo it. And Pulsar Functions, as we see, eliminates the need for that boilerplate code. It handles all of that producer and consumer setup for you and allows you to just focus on the business logic itself. So now that we've seen the bad way of doing it, or the old way of doing it, or the hard way of doing it, let's look a little bit about Pulsar Functions, right? And how that programming model works and some of the benefits of it over traditional application development we saw in the previous section, right? So Pulsar Functions, what are they? If I had to define them simply, I would say they're a Lambda style function that uses Pulsar as the underlying message bus, right? So, and by default, as I mentioned, it handles the setup and the producer, the consumer for you, the creation of the client, so that you don't have to write all that boilerplate code, right? And what it does is apply user-supplied logic against a consumed message. So as you can see in this diagram here on the right-hand side, you can have multiple input topics coming in, and those input messages are fed to the Pulsar function, who can then, again, applies whatever business logic you want on it and optionally produces an output topic if it wants to. It can also just return void and do nothing, but it does some sort of business logic and then can feed it on automatically as a return value to an output topic. It also has the support for a log topic if you want to sort of log your information and do some metrics collections, things of that nature. All of that's provided for you easily. So this blue box here is really just your user code and nothing else. So as we saw in the previously, right? So why do we want to use Pulsar Functions? All of this, as we saw this boilerplate code, all of this set up, these 16 plus lines of logic to connect to a topic, to consume it, to be able to write a result based on the business logic around here. This all simplifies to this using a Pulsar function, right? And so you can see now all we have is the business logic itself. And by implementing this interface here, this function interface, you basically, when you submit it as a Pulsar function, all the incoming messages are passing to the function one by one. So as you can see here, you're specifying the function takes an input of type string, and produces an output of type string. And so you automatically can basically take that method there, and those input messages come in as the input in that parameter there in the apply method, which is defined in that Java util function API method there, and it returns a string. So all you have to do is just return, when you return that value, it's automatically published to the output topic as well. So you can simplify your logic as well and focus just on what this business logic is, right? So that's some of the benefits. Again, just to reiterate it, you focus on the business logic. It sets up the producer and consumer for you. All that's done transparently as part of the framework, and it handles the message consumption and publication for you. And as you notice, it may also do auto acknowledgement of the message, so that you can see the message acknowledgement can be set up to be done automatically on your behalf for you, and they can run as threads, processes, or Kubernetes pods inside Pulsar itself. So there's no need for another application processing framework, and they can be scaled up independently. So if you imagine back to the previous application where we had one particular set of code or large monolithic code that had multiple different services within it as different classes, and you needed to scale that up, and that was running as a process, and you needed to increase the throughput of one of those, you'd have to multiply the number of processes each in order to achieve that throughput. Where with Pulsar Functions, you can say, just this particular service, I want 5 instances of it running or 8 instances of it running, and the other ones can stay at 1. And so it allows you to a lot more flexibility as far as deployment goes. So let's focus a little bit about microservices and just reiterate, what the architectural style is, some of the benefits that it hopes to achieve, and hopefully how Pulsar Functions can help you develop these microservices. So I'm sure most of you are familiar with it, what microservices are. It's been pretty prevalent in the application development community for over almost a decade now. Basically, it's a result of a style of decomposing an application into a much smaller suite of services or pieces that can each run as its own process and communicate with one another via lightweight mechanisms such as HTTP or messaging. So it's traditionally thought of as take the monolith, one big like e-commerce application that has order entry, order fulfillment, payment fulfillment, and dispatch and tracking all in one big blob of code that has to be updated. When you want to have any one of those services, you have to update and redeploy the whole thing. You break it down into several services that do perform those same tasks separately, and they interact with one another, by passaging messages or calling one another in order to achieve the same result. And so one of the goals of breaking it down into that, using microservices of that was, obviously having highly maintainable and testable code, right? Break it down into smaller chunks, and they're loosely coupled with one another, so they can be developed independently. You can change database schemas that are used underneath the covers, and so they're not tied to, closely tied to one another at the back end level through database structure, things of that nature. They're independently deployable. So again, you could, if there's a bug in one or you need to update one, you can just fix that one quickly and deploy that one, and it will not impact you don't have to take down all the other services in order to do it. And typically it's characterized by being, developed by a small team, as Amazon's famously called, the 2 pizza rule. If you have a meeting and there's 2 pizzas, that's enough to feed your team. That's the right size team. And that's really what you're looking to achieve with microservices. So you can have small, nimble groups all acting independently and streamlining the development process. And having a faster iterative processes are the goals of microservices, right? So obviously, for microservice architecture to work, the services have to be able to interact with one another, right? You're breaking this large monolithic down into smaller services, or you're building up from scratch. You have these multiple services. Obviously, they have to communicate with one another, right? So there's these multiple different, I show this Venn diagram here to say there's different communication styles and how they're supported, right? So there's synchronous and asynchronous communication. Obviously, are 2 different, is one, metric that you can look at. And then if you're sending from one receiver or multiple receivers is the other sort of concept of how you're doing that. And in this overlay, you can see that messaging is actually, if you're using the traditional REST or gRPC method, it's always designed to be like a remote procedure called one-to-one. The order entry service sends a message to the payment service and it waits for a response. And when it gets that response, then it can move on with that response and do something else with it. Maybe, say, okay, the order is accepted. Now let's go to the order fulfillment and send a message, right? So it's a very serial stage-based processing. But with all the other messaging, all of these messaging patterns are supported, or all these messaging communication styles are supported by messaging, right? You can do synchronous, asynchronous, multiple, not multiple, synchronous communication using messaging. So it's a much more flexible pattern, which is why I think it's a better approach than using the traditional RPC method. So we can think about, we can see some messages here. I can eat a whole pizza with half a team. Yeah, that's great. I know how that is. So we're looking at microservices deployment and composition. So you can think of these microservices can be composed of several subservices underneath the covers, right? So they typically run as individual processes, but they can also be comprised of multiple processes that are always developed and deployed together, right? So you really want to have, you usually have more than one block of code. And one of the classical examples, okay, I have an application and I have its own siloed database as well. And that's a traditional, and that prevents that leakage or that from the codependency from your schema changes. And that's a classical example of having multiple applications tied together, but thinking of them logically as a service, right? So they can be further broken down is the key takeaway from the slide. Your service can consist of multiple services, which consist of multiple services, and so on and so on. So having said that, let's look at why I think Pulsar functions are a good fit for microservices, right? Let's go back to the desired characteristics that we're looking for and see how Pulsar functions applies or provides it, right? So you're looking for something that's highly maintainable and testable, right? Well, Pulsar functions are small pieces of code that can be written in your traditional popular programming languages. So they're easily maintained in source control and can be tested with existing frameworks, right? If it's a simple function, you can use, JUnit, test and easily test it, independently. You don't have to worry about that. They're loosely coupled with other services, right? So Pulsar functions are not directly linked to one another. They communicate via messages. So again, their API is, I'm getting a message of this type and I'm publishing a message of this type. So there is no other codependency between them. Sometimes you can use, as you'll see, a shared schema, but that's traditionally a shared library that can be deployed across multiple services, and they all bring it as an import instead. Third point you want looking for is independently deployable, right? So they are designed to be deployed independently. Each Pulsar function is its own pod. It runs its own pod or thread, and it can be deployed independently as a single jar. So you bundle everything up that's part of that service, and then you can just deploy it. A goal that can be developed by a small team. Obviously, they're often developed by a single developer. The logic is so simple that a basic, first-year intern can write these it's the most primitive logic you have. Again, it's a Lambda single function, right? You have one block of code you have to do. You can break it down into smaller pieces, but at the end of the day, they're about the right size for a single developer. Team development usually doesn't get that much, that isn't really involved in a Pulsar function. Inter-service communication, right? We saw the need for inter-service communication, right? So Pulsar functions support all your messaging patterns using Pulsar as an underlying messaging bus, right? So you can have, as we mentioned, that communication style, one-to-many, asynchronous, point-to-point, all those different things can be done using Pulsar functions. And again, you're automatically wired into the Pulsar messaging bus. And so that's pretty much given to you for free. And then lastly, deployment and composition. As I mentioned earlier, they can be deployed as threads, processes, KS pods. So they can run KH pods, so they can run independently. And we also have this thing called Pulsar function mesh, which allows you, if you logically have to group them as 5 or 6, you can sort of specify that and deploy them as a single unit if you want. It's another feature that Pulsar provides. I won't get into it in this details. If you want some more information, there's information online. I'd be glad to share that with you at the end of this presentation. So let's look at a very simple, I've talked about it a lot. Let's just look at it. Let's just look at the code and see what a simple, again, this is a very simplistic version, but this would be like a sales tax calculation service, right? This is it. So if you had an e-commerce site and you wanted to be able to, okay, I have the final shopping cart total, but I want to calculate the sales tax. So you hand that off to another function. This is it. So this is about as simple as you get as far as code. Obviously, it's easily testable, maintainable, deployable, et cetera, right? Obviously, it's bad coding practice to use a constant, but this is more to show you a feel for how big or how small, like this is like the minimum Pulsar function that you can have, and it's very, very simple to use. But it is also serves a useful purpose, right? So you can quickly swap this out to have a lookup table, have a state come in. So you have a schema that has an amount and a state come in, and you can look up the table and provide that as well. So it's very flexible, but it sort of gives you an idea of how you can restructure your microservices as a Pulsar function. So having done the background a little bit, I know Giannis is going to be pressed for time on this. Let's look into a little bit about designing an event-based microservice and how you want to take a logical business problem and break it down into the microservices that you'd apply to solve that problem, right? And talk a little bit about the role that schemas play in a microservice application. And then at the end, sort of give you an outline of the microservices based application that Giannis will show us how to develop at the end of this module, or at the end of this webinar rather. So just to give a rough definition, make sure we're on the same terms. When I'm saying event-based microservices, I'm saying anything that uses a message bus to communicate, I refer to as an event-driven architecture. So the key to characteristics of an event-driven architecture is when a service performs a piece of work in response to an event. So an event comes in, the service gets triggered, and then it creates some output that other services might be interested in, right? So one or many, again, that's that one-to-many communication protocol. And it produces an output as an event. So then other services can then consume those events so that they can perform their tasks as well. So it becomes a staged event processing scenario where a message comes in, I do some enrichment, those enriched messages can then be processed by other events that can then do lookups and then call it and so on and so forth. So it becomes a very staged, but every event, every service along the way adds value to those events and passes it through or does some reaction based on that communication, right? And the messages are stored in intermediate topics to prevent message loss, right? So unlike the gRPC, where you're doing it over the network and you have to wait for for it to time out to realize that it didn't get sent. With an event-based messaging protocol, you can do a fire and forget, right? So you can just, I'm done with my message, I've published it here. When the people come around to read it, they can come around and get it whenever. So if a service fails in the middle of processing one, that message remains in the topic, right? So think of the RPC scenario where you send it over the wire, the service gets it and acknowledges it asynchronously, it tries to do some processing and fails. You lost the fact that you no longer process that message or that event. So it has an intermediate store is the key takeaway, and you don't lose messages and everything gets reacted to using those topics as the intermediate exchange of communication of data, right? So a perfect example, again, of a microservices, event-based microservices is when an order is placed at an e-commerce site and a single order placed event is produced and then consumed by several microservices, right? Which is sort of the example we show here, right? So in order services, say one service is going to take that same record and update a database. A fulfillment service is going to look at that information and maybe say, okay, I got to go get the customer record and get some delivery and payment information. And then the payment service could also, okay, I have to take this credit card information, whatever, and go to a third-party payment processor to secure funds and make sure everything is secure. And so you can see multiple different services doing different things based on that one event. Is sort of a classic example of microservices, event-driven microservice. So now enough with the theory. Let's look a little bit about our specific use case and what we're going to show today. And for those of you who have read my book, you might recognize this one a little bit. This is the example I used throughout Pulsar in Action, but it's based on a hypothetical food delivery service. So think of it like, different services we've used throughout the pandemic to feed ourselves. We want to stay at home and stay safe. But again, it's a basic order entry and it involves several different microservices, right? So a customer would have a mobile application on their phone. And eventually once they've gone into the user interface and they've picked it, they want to order pizza and some soda, maybe a salad, whatever. And they go ahead and they submit that, publish that order, it goes to the customer order topic. Well, obviously those messages get sent there. We have a order validation service that we'll get into a little bit that takes that information and processes it and kicks it all off. But as you can see, every step along the way to get it from I place the order, assuming it's about a topic, we select a restaurant, we notify the restaurant so they can start preparing the food. Once the food is prepared, the restaurants can then trigger an event to notify the drivers to say, hey, we got to find somebody to pick this order up and deliver it. And then you go to the order solicitation service that notifies a subset of the drivers to say, hey, we've got an order for you, who wants it? First one to pick it up wins, and then they get notified to pick it on and so on and so forth. So this is sort of a very simple handoff of the order, the food order delivery use case in this scenario. So having said that, let's talk a little bit about schema design, right? As you saw in that previous definition, we have a lot of services interacting with one another, and each service sort of has to know what information it's going to get, right? So we want to be able to design a schema. We're going to design schemas so that every service is on the same page as far as what information is being passed, right? So let's go back a little bit here, backtrack a little bit. The order validation service, for example, has to know what the food order looks like. We need to know what an address looks like. We need to know what the payment information looks like, and all that is communicated via schemas. And so we're going to show, Giannis is going to show how we use the Avro interface definition language to sort of define these schemas, and then a little bit about schema compatibility and when you need to make changes, if it's a breaking change or not to the existing services. So you can think of microservices, when they communicate, they have the agreed upon basic structure, what those messages are, including the fields and their associated types, right? So again, I'm telling you, it's a payment type. So it's a credit card in this field, that's going to be a string. This is the payment type. It's a float. This is an enum of the credit card type it is, for example, Visa, MasterCard, Discover, et cetera. And so that metadata defines the structure of the messages, and it's common, and that's referred to as a message schema. And they form an informal contract between the services, right? So I'm expecting as that order validation service to get data in a certain way. And if I don't see it that way, I can't do my job. I can't function properly, right? So it's useful to think of those message schemas as the APIs between those microservices themselves. In the traditional gRPC framework, that API is through method calls, right? It's explicit method calls. I'm making this one. Here's the parameters. Here's their position. Here's their type. Message schemas form that same function as far as enforcing the contract, right? And so the applications that depend on these API and if any changes are made, you want to make sure that they're still compatible, right? You don't want to make breaking changes. Again, the key to microservices development is independent development. So some team might decide, hey, we need to add something to the menu item, for example, but we don't want to, by changing that schema, we don't want to break the order validation, right? They need to be aware of it. So that's something that you have to be able to, coordinate. That's your key coordination point across microservices when you're using event-driven and message-driven microservices development. So when you're designing your API, your microservice message, keep these are some of the specific considerations to keep in mind, right? You don't want to leak internal implementation details or mirror an internal database, right? Because again, that's that exposure of the database schema sort of leaking out into your message structure. And then when you ever need to change that database, all of your schemas are going to break, right? So you want to sort of have a layer of insulation from that. Just don't copy a schema out and say, database schema, say this is my message type. That's a bad approach. Again, any events are typically, domain events. Think of them as logically the way you would structure events and do, detailed domain design back in the day, and you have a logical structure or logical model of the domain, right? It's a contract between the services, and you should only change it when new functionality is needed. So don't willy-nilly, change the address type or change, food order type without, a very good reason. And design your API in a way so that there's room to grow and evolve. So consider using versioning of the scheme and developing backward compatible APIs, right? So have a V1, a V2, a V3, a V4 of each type, and make sure that the V2 type of that message, for those that are still consuming those, can still function with a version 3 of that schema type. So again, if you add a field to an address field, for example, and that becomes version 2, as long as you're adding in that field, the old ones will be able to still work because you haven't taken anything away, but they won't have access to that newer field that's available. So keep that in mind when you're designing your messages. So having said all that, getting down to the specifics, we decided to use an IDL instead, because it's more of an abstract layer than writing those classes by hand rather than writing a food order item, a menu item, things of that nature. We're going to define them using a schema and then use a tool to generate that for us instead, right? So we can generate the client code. It handles all the serialization code for us as well, and API and documentation as well. And, Avro supports multiple schema types. It does JSON, Avro, as well, and protobuf is coming. It's not quite there yet. So Avro IDL is a great option, and we're going to use that for this exercise as well. And we can sort of hand this off to Giannis, but he's going to show you this as well. But this is an example of what a schema definition would be, just an example of how you define that very easily. I want to make some key points here is that you can import other ones, right? So you can have a different specialized geographical IDL for just your geographical objects like addresses, things of that nature, and import them. Same with payments and restaurants. Everybody can have their own, but then you can easily import them and use them across different items. So it becomes very easy to maintain, and they can evolve naturally within their own substructure of where they're logically fit as within the object domain. And this is just an example of that. So without further ado, I'm going to stop here and hand it over to my co-host Giannis, who's itching to show you some code on developing the microservices and just getting into the gory details of that.
Thank you, David. So let me just share my screen. Okay. Can you guys see my screen all right?
Yes, we can.
Yeah, so this is what we're going to be building. So this is our order validation service over here, which is basically comprised of 5 different microservices. So on the left, we have our source input that generates data inside our food orders topic. And over here, we have the order validation service, which implements the splitter pattern. And so it sends, it forwards the messages on 3 different microservices. The one that does some payment validation, the one that does some geo-encoding, and the restaurant service that communicates with the restaurants and provides some ETA. And so then we have the order aggregation service that gathers the results from all the services and basically forwards the messages forward, whether the order was accepted or it was declined. And so, as David mentioned, the first thing you might want to think about is also how you want to define the schema. And over here under the resources and Avro folder, we have our Avro schema definition files. And this is how we specify the schema for each of our microservices. This one is for the food orders. This is one for the payload for the geo-encoding service. The one for the payment service, and this one holds information about the restaurants. And after you have created all your schema definition files, then with Java, for example, you can use the Maven plugin, the Avro Maven plugin over here, where you basically specify the resources directory for your Avro files, which is located over here. And we also specify the output directory for our project is the root Java project. And since we are also specifying namespaces inside our definition files, everything is going to be created under this package over here. And so for the second demonstration, I'm going to delete this folder here. And if we run the basic Maven clean command, install command, after the compilation finishes, we should be able to see our schema files are created here. Let's give it a little while. Boom. Okay, that's strange. Oh, I should have. This is the wrong directory. Sorry, apologies for this, guys. I should rerun this command. So as you can see, we have our classes generated for us here based on the Avro schema definition files. And so if we take a look inside one of these classes, we can see the result of metadata, which basically specifies how the records be serialized and deserialized, the fields provided in the class, as well as it creates a builder pattern for us. And so with our schema in place, then let's review our architecture again. In this part 1 series, we're going to be concerned only with the order validation service and with generating some records inside our Apache Pulsar topic. So for the sake of demonstration, we have provided some producers over here, but as David mentioned, it's a lot of boilerplate code. So for that reason, we're going to leverage the Pulsar IO framework and the source interface over here, which is used for integrating with external systems. For this part series, we're not going to integrate with any external system, We're just going to emit some mock records inside our Apache Pulsar topic, but in general, it's a simple interface that provides the open and read methods. The open method is triggered once when the connector starts, and over here, typically you might want to create some external connection with some external system. And then there is this read method where we are going to generate some mock data with a small delay. So moving forward to our validation service, as we saw in the slides, it's a matter of implementing this function interface here, which is strongly typed. And for the input, we're going to provide a food order. And because we want to do some manual routing to involve different microservices, the output type is specified as void. And for that reason, we return null here. And for each incoming record, for each food order, we want to extract the order ID here, the delivery, the address of the food order, as well as the payment information. And each one is going to be sent on different topics to invoke different microservices. We have the address being sent, the delivery location being sent to the geoencoder topic. We have the payment information being sent to the payments topic, and the whole food order is sent to the restaurants topic. And lastly, we also send the order ID to the aggregation service so that we can notify that a new order is in place, and we're waiting for the aggregation of the results. So after we have developed our function over here, the next thing we want to do is generate a jar, a fat jar out of it. And we have two options. We can use an R file or a jar file. Over here, we're just generating this jar file over here that creates everything. And with these things in place, we want to take a look at how we're going to deploy microservices. So with Pulsar Functions, you always need to specify the configuration for your function. And this is done by using some YAML configuration files, where in general, there are some required parameters and some of them are optional. So for the validation service, we need to specify the full qualified class name over here, along with the tenant and namespace we want our functions to be deployed inside. We provide the name for the function, the input topic, how many instances we want, and then we can provide optionally a log topic where the logs of the service are aggregated inside. We provide note acknowledgement for each message, a subscription name. We want to clean up the subscription number after our function is stopped. We specify its of type and the resources for our function. And the same logic applies for the source connector. It's basically the same configuration file, only this is smaller. And we also specify the processing guarantees here for demonstration purposes. And at least once is the default one parameter, but you can also use at most ones or effective ones based on your needs. And let me just, now that we have everything in place, let's go and deploy these functions. And so let me just take this out of the way. And so as you can see, I have my Kubernetes cluster up and running here. We're going to deploy everything inside of Kubernetes. And for the sake of simplicity, I have provided some scripts along. We have this setup script that all it does is it packages our application, it generates this file over here, this jar file, and it copies the function directory along with jar file. Apologies for that. Inside our toolset code over here. So when you want to experiment and play around with yourselves, you can use the script. Just make sure that the pod name over here for the toolset is the one matching the one you have on your cluster. And my letters are way too big, but it should be somewhere here, the toolset code. Yep. This one, make sure it's the right one, as well as the namespace parameter specified here. So this deploys everything. This uploads everything inside the toolset code. And let me just open a terminal inside the code. And as you can see at this point, I have this functions config folder that contains all of our configuration files. And along with that, I have my jars folder that contains the workshop jar. And what we're going to do now is we're going to take our function source connector and deploy them. And for that, I have provided also a deploy shell script. We're going to comment these things out for now because we're going to be concerned with this in part 2. And all it does, it executes inside the toolset code the Pulsar admin functions create command, where you need to specify the function configuration file for your function, as well as the jar file that it's going to use. And the same applies for the source connector. So inside my terminal over here, if I run this deploy shell script, you can see that both the function as well as the source connector is going to be deployed as a Pulsar pod, as a Kubernetes pod. And when the source connector starts running and we check the logs of the validation function, we should see that messages will be arriving and being processed from that function. As you can see, we have some mock food order records arriving constantly, and we're going to continue doing some further processing on that. Again, for part 1, we are only going to be concerned with this part of the architecture. And when you deploy your source connector and your Pulsar function, there are some commands you might want to use to check the status of your function, as well as some statistics. The first one is the Pulsar admin functions status command, where you need to specify the name of the function. And for this one, it's validation func. And this is going to give you some insight on whether your connectors started successfully, if there were any errors, or how many instances you're supposed to have, how many are running, some general information. And the other command is the stats command, which you might want to use to retrieve some metrics and statistics about your functions. So you can see here, it provides some statistics about your function running, like how many messages were received, how many were processed, etc., etc. And so, yeah, I think this concludes our presentation for part 1 of the webinar series. And I think we have a few minutes for questions. David?
Great job, Giannis. Thank you so much for that. I'm going to go back to that. So we'll open up the floor to questions now. If anybody has questions, you can post them in the Slack. I'm sorry, in the chat. So use the Slack.
Okay, so we either did a really good job or there are no questions, but hopefully, I hope that you guys learned something useful today. Oh, I just realized my camera was closed all this time. Apologies for that.
Also wanted to share these links with anyone who's interested in following the code themselves. They can download it here that Giannis went through. I know he went through quite a bit, and there's a lot of good content there, so you can access that information there and try it yourself. You can go to our LinkedIn site for more information, follow us on Twitter, watch a lot of our YouTube information as well, or go to our website, and there's lots of resources there as well. I think I see a couple messages as well. We have some new ones. Let's see what we've got here. So,
yeah. So in general, Pulsar supports for Pulsar functions supports JVM languages, Go and Python, but we have many other client libraries. I mean, I think, David, you saw it in some slide, but there are also some third-party libraries like for Scala and Rust, I think.
Yep.
Community, yeah, there is a lot of work going on, and many new libraries are popping up all the time.
Yeah, absolutely. And another alternative would be, again, you could go back to the traditional style we showed in module 0 using a traditional language like Node.js or something where you can have a client and you could do you could add that boilerplate and handle that as well. So if you wanted to do Pulsar functions using a language outside of the ones that are a microservice outside of that, you could resort to that as well. But Pulsar functions currently supported by Java, Python, and Go at the moment. Use cases about Python on the website so you can share. I do have some Python examples in my code repository associated with my book, and I'll be glad to direct you to those as well. Just full disclosure, the Python functions piece is not as fully vetted as the Java one. The Java one is further along, so I tended to focus on that one just because it's more complete and more tested, but I'll be glad to share that with you as well. Yeah, absolutely.
And also I think the time series part would be really good with Python as well.
Yep.
It's my favorite thing with David, how he does edge analytics on top of Pulsar.
Great. Yep. Thanks, Tim, for sharing that GitHub repo for the Python examples. There are some there with Pulsar functions. Yep. Mr. On the spot. Thank you.
Nice. Well, I'm seeing that the questions are starting to taper off a bit and we're coming up on top of the hour. So I just wanted to chime in and say, everyone, thank you so much for joining in with us today. Oh, here's one more. Any testing tool list for Pulsar?
So again, you can use the traditional like JUnit, Python unit testing. There's also something called a local runner that you can run Pulsar functions locally on your machine and have a debugger, and it interacts with an existing Pulsar function. So basically what it does, again, I mentioned earlier, Pulsar functions run inside or on top of Pulsar itself, but that makes it hard to test them and debug them. So there's this tool called local runner that's part of the build where it allows you to run the function locally on your machine that gets and receives messages from the broker running somewhere else, but you can set breakpoints and step through your code as well. So if you're having any sort of issues, you can use that as a great tool for integration testing as well. Yeah, there is test container support for Pulsar, so you can spin it up and do automated tests. We use test containers as part of the Pulsar build itself. If you go into the Apache repo, we have some of our tests are completely run using test containers. That is correct.
And let me just reshare my screen again. Inside our repository over here, you can find some examples for testing with local runner for every function and the source connector. Some basic testing, but you can take this as a first approach and start exploring how you can use the local runner for testing against your Pulsar cluster. Everything, again, is inside our GitHub repository.
Perfect. Another one coming in. It looks like, what do you recommend for monitoring and tracing?
So yeah, that's a great question. So by default, again, the running is Kubernetes pods. You have the Kubernetes tooling. There's also all those metrics that Yana showed you are published to Prometheus, and so you can set up any sort of alerting tool to ingest those metrics and monitor, throughput, processing latency, as you saw there, right? So your average latency starts spiking. You can automatically spin up some more instances as well. Yeah, I think those would be the biggest tools that I could recommend. There's also a way within the context itself, you can publish your own metrics as well as around number of messages processed as well and create your own metrics as well. So it's a very flexible framework to add your additional tooling and instrumentation as well if you wanted to do so. And there's some documentation on that as well. Yeah.
Okay.
Perfect. Amos, I see your comment in here also. Dawn is actually the development head for all of our training. I'll have her reach out to you directly. I believe I've got your email in here also with your question.
fair point, though.
Mhm.
Yep, very fair point.
Yep.
Well,
Okay.
thank you everyone for attending. Yeah, Karen.
Definitely. Big thanks, David, Giannis. Thank you so much for sharing your expertise, taking us through both the use case and the hands-on demo. Also, Tim, thank you for helping out on the chat line. Everyone, we'd love to see you for part 2, Stateful Microservices. That's going to be happening next week on September 15th. Your registration should have allowed for your login for that as well. If not, we'll be getting in touch with you shortly with it. And if you found this as interesting and valuable as I did, please share the registration page with your peers, teammates, team members, things of that nature also. I'll go ahead and put that link back in the chat also. A recording should be available for everyone shortly. Thank you all again. Appreciate you being here.
Okay.
Thanks.
Thanks, everyone.
Guys.